Okay, thanks.
Feel sick for that last 30 minutes. That car is either a rocket ship or a piece of shit. Felt so bad. Well, that's actually really crappy because now it shows that you didn't have a retirement.
Do you think you pass it?
So the statistics are
We'll see how he does his questions. Quite a few things for that to explain sufficiently.
He's your buddy, right? No problem. All right, well, he was a decent driver. The Ferrari was a piece of shit. Had time to screw up. Because they're getting Russ Brown. Oh, no, he's from Marlboro or something. Yeah. The
principals are.
No, but even yesterday, this guy's were on
Yeah, I think Good morning, everyone. Thank you for coming to this presentation. This morning we have the final public oral examination for Tyler Abrams for his thesis entitled Erosion and Redeposition of Lithium and Boron Coatings Under High Flux Plasma Bombardment. There you go.
Okay. How's the volume? Is that all right?
Perfect.
Okay.
Great.
First announcement, there are cookies in the back, so I won't be offended if you get up while I'm talking and go get a cookie made by my Alex. So, good morning and welcome. Thank you for coming. As Mike mentioned, my title is The Erosion and Redeposition of Lithium and Boron Coatings Under High Flux Plasma Bombardment. My advisors are Mike Jaworski and Bob Kaida, so tremendous gratitude is due to them for all of the assistance and help and support that they have given me throughout the last 5.5 years or so. There's also a lot of other people that I want to acknowledge. I'm not going to read through all of these names, don't worry, but particularly I'd like to acknowledge the people in bold. Gregory de Temmerman was sort of my European advisor over at Magnum PSI. Dave Ruzick at Illinois, J.P. Elaine and Russ Dorner were sort of the inspiration behind a lot of this work on temperature-dependent erosion. Princeton University, Mohan Chen for a lot of the simulations, Bruce Kale for very useful discussions, Rob Goldston and Darren Stotler for being committee members and also teaching me quite a bit about plasma material interactions, and Charles Skinner for being a reader of this thesis and also helping me out quite a bit. Oh, and also, of course, Barbara and Beth for all of the myriad of things they do for the graduate students. So, a brief outline. I'll first discuss the introduction and the motivation for this work, tell you why you should care about plasma material interactions, why they're important in the context of fusion. Then I'll talk about sort of the meat of this work, which is on lithium erosion under high flux plasma bombardment, which had really never sort of been studied before in such a quantitative and high resolution way, and I'll explain what I mean by that later on. And then I'll get into measurements of lithium redeposition. I'll tell you what that means on a couple slides. I'll tell you about erosion of boron coatings as well, and then finally I'll discuss and attempt to draw some conclusions. So first off, why do we want to study the erosion and the redeposition of lithium and boron? Well, it's because we apply these coatings to the walls of tokamaks, and when we do, it increases the plasma performance and also reduces what's called ELMs, which are these very periodic bursts of energy that are expelled from the plasma that you see down with these d-alpha traces at the bottom here. So increasing lithium coverage reduces ELMs, and it also increases the stored energy in the plasma. And in addition to this, it actually has been observed to protect the porous substrates that it resides in from the high heat fluxes of plasma bombardment. So for these reasons, it has been proposed to actually use a liquid lithium surface as an alternative to a high-Z solid material such as tungsten in an actual fusion reactor, which we usually call demo, a demonstration fusion reactor. And the advantages of lithium are that, as I mentioned, it's self-healing under plasma bombardment. Since it's already a liquid, you can't melt what you've already melted. And if you do deplete the coating by lithium erosion, then you can actually replenish the material by simply flowing it back onto the wall. However, just to give you sort of a motivation for the existing issues associated with lithium erosion, there have been studies done of the erosion, the temperature-dependent erosion of lithium under lower flux plasma bombardment. The Pisces B experiment has fluxes in the 10 to 21 per meter squared per second range. And the evaporation and the temperature-dependent sputtering, well, I'll explain those a bit more later, was observed to actually increase very strongly as a function of temperature. And the atomic lithium yield, which is the fraction of lithium atoms that come off of the surface divided by the incident ion flux, actually goes to almost 10, about 5 or 6 by about 400 to 500 degrees C. And reactor diverter temperatures are expected to reach at least 600, 700, even 800 degrees C. So as you can see, these various models, don't worry too much about all these different parameters right now. I'll explain them a little bit more in a couple slides. But just see that the temperature-dependent erosion rate, which is given by Y, this yield, is expected to scale exponentially with temperature. And the scalings for these are a little bit different for the thermal spike model and the atom sublimation model. But they both increase exponentially with temperature, which is it provides very pessimistic estimates of what temperature you can reach with a lithium plasma-facing component. So, to summarize, low-Z coatings improve plasma performance. However, they have to be replenished before being depleted by a plasma bombardment. So, it is crucial to develop a predictive capability for how long these coatings will last. And this task has been recognized as an important research thrust, a scientific grand challenge, and a Tier 1 initiative in various reports by the U.S. Fusion Energy Sciences Advisory Committee. So lots of people think that this task is very important and worthy of study.
Low-Z coatings?
Yes, low-Z coatings.
At high priority by PSAC?
They were specifically listed in at least in this scientific grand challenge, or no, in the important research thrust. Yeah. They specifically mentioned low-Z coatings. I think in 2014 they just call it taming the plasma material interface. Okay, so now on to the theory. So I've drawn this cartoon right here. I know it looks complicated, but I'm going to go through this one point at a time. So these are all the relevant processes that I needed to study in the context of deuterium-lithium plasma surface interactions. So up here is the near-surface plasma, and down here is the mixed material lithium-deuterium material. And so the different reactions you can have are deuterium ions incident on the surface and knocking off atoms from the surface, which is known as sputtering. If you have a mixed material, some atoms can actually be sputtered more efficiently than others, which is known as preferential sputtering. You can have ionization occurring in the near-surface plasma, which is where an electron is knocked off the atom. And then this ionized atom follows the magnetic field lines back to the surface in a process known as redeposition. Atoms can also form what are called add-atoms on the surface, which is basically an atom is knocked out of its state in the lattice by a incoming energetic ion. It forms a weakly bound, quote, add-atom on the surface, which diffuses around. It can find a vacancy and recombine into the material, or it can be evaporated or sublimated off into the plasma. These atoms can emit line radiation. They can recombine or charge exchange to form neutral atoms. These are not the same process. These processes don't happen simultaneously. I just drew them here together to save space. And then in the material, you can have a number of things going on. You can have chemistry effects, such as adsorption, which is basically when an atom chemically binds to a surface, or well, either chemically or just is physically implanted into a surface. You can have formation of lithium deuteride. Because lithium is an alkali metal, it reacts very readily with hydrogen, and so it forms the lithium deuteride compound. And then you can also have diffusion of these deuterium atoms deep into the bulk of the lithium layer. And it's been observed in experiments that this will actually occur in up to a 1-to-1 lithium-deuterium ratio. So I'm going to talk about a lot of these processes in a little bit more detail. I'm going to start by talking about the deuterium diffusion in lithium. So until very recently, nobody had really characterized the deuterium diffusion as a function of the deuterium concentration in the surface as well as the temperature. The only existing result was one experimental result from a very small concentration of tritium in the material. So these simulations were molecular dynamic simulations performed by a group on campus led by Mohan Chen and Emily Carter, his advisor. And they calculated the diffusivity of the deuterium and lithium versus temperature and the concentration, which I call beta. And as you can see, they're given over here on the left. And the decrease here is due to the increasing concentration of deuterium in the lithium. And this bottom teal line here actually corresponds to complete what I call saturation, which is a 1-to-1 lithium-deuterium ratio on the surface. So the diffusion coefficients clearly decrease very strongly versus concentration, as well as increasing versus temperature. And the reason that you sort of have this discontinuity in the behavior of the erosion rates here is due to the solidification of lithium deuteride. Lithium deuteride is a solid for much higher temperatures than pure lithium. So you expect the diffusivity not to increase until the lithium deuteride liquefies, which occurs at a temperature of about 1000 K. So with these diffusivities in hand, you can actually solve for the time-dependent and temperature-dependent deuterium to lithium concentration in essentially any material if you know the implantation rate of the deuterium atoms in the lithium material. So we were mostly concerned with relatively thin coatings, and so by thin I mean that the thickness of these coatings is much, much smaller than sort of the surface area. So you just can do this in 1D with a 1D diffusion equation, just fixed law, which is given right here. And so for our purposes, I just assume the deuterium is implanted uniformly in the top 5 nanometers, and then you establish the boundary conditions that the deuterium can't diffuse back out into the plasma or into the substrate underneath. And what we are interested in is if you expose the lithium layer to some constant fluence of deuterium atoms, but at varying fluxes, how does the concentration of deuterium atoms beta on the surface change as a function of flux? So at low fluxes, you expect, since the implantation is happening so slowly, the deuterium will just be readily absorbed by the lithium, and it'll establish a uniform concentration profile as a function of depth. But then at very high fluxes, the deuterium actually begins to bombard the surface faster than the liquid lithium can absorb it without a sort of runaway increase in the deuterium concentration. So this was for a 100 micron thick lithium film at 400 C, just a constant temperature. And it's just sort of a cartoon to demonstrate that you actually do get an enhancement of the saturation even sort of in real time as a function of the deuterium flux. And so the experiments I'm going to show you about are sort of in this range of flux. And the predicted fluxes in the diverter of a fusion reactor are down here. There is some overlap between the two.
That's for a constant fluence for each of those data points?
Yeah, it's 10 to the 23 per meter squared for each one.
Did you find that if you went to higher fluences on the higher flux cases that the runaway effect continued, or is there a ceiling that it reaches?
So essentially where you're going to see this knee is it seems to be about where the flux times 1 second is equal to the fluence. So for higher fluences, it might be like more like this. I would have to go look, though, to be sure. It takes a long time to do these because I'm not using a very good algorithm.
So that equation you have on that blue equation is funny in that one might have expected d to be inside the first derivative, so d by dx of d by dx of beta. And also, beta is a funny object. It's not the lithium, the deuterium lithium concentration. I guess. What is this?
It's the deuterium. So it's the deuterium concentration divided by the lithium concentration.
Right. So when that gets to be of order, 30% or something, it's not just the deuterium density. So could you?
Right, but you're basically just. I mean, all I did was take the existing density and just divide it by the lithium density, which is constant.
Well, it isn't if it's all been displaced by deuterium, is it?
So you're assuming that the lithium, you're essentially, right, so this is making the approximation that the lithium is staying where it is, so the material's not changing density, basically, atomic density.
Lithium atomic density.
Right.
And that's what happens?
That's the assumption about what happens.
Related question, what is the justification for the d beta dx equals 0 at the surface? What's the physics?
That's physically saying that, so that's just saying that the lithium does not diffuse back, or the deuterium rather, does not desorb or diffuse back out into the vacuum.
But why can you assume that? I mean, why can't you have a gradient of the deuterium density from the front surface into the depth?
You could do that, but the fact that it's being, so there's also some implantation rate going on right here, and so that's really going to dominate any desorption that's going on back out into the vacuum. Maybe not at the very low fluxes, but for sort of these kind of relevant cases, it's being bombarded with deuterium so fast right at the surface that it doesn't really matter.
Your whole diffusion equation assumes that there's no beta gradient, right? Otherwise you'd have a derivative of dD.
It only assumes that those are the boundary conditions. It only assumes that right at the boundaries.
But you're after the point that d is a function of beta, and that should be
And
inside.
beta has a gradient, so it should be, like you said, inside the derivatives. You're forcing it to have zero gradient in the equation and at the surface. It may not matter for your subsequent analysis, it's just a little weird.
Fair enough. Okay, so now we have some approximation for what the calculation is for the concentration as a function of time and fluence and flux and temperature. And so we want to know, how does this actually affect the lithium erosion rate? Well, the adsorption and implantation of deuterium into a lithium surface is expected to reduce lithium sputtering in two ways. So the first one is called preferential sputtering, which I mentioned earlier, which is essentially you have a dilution of lithium atoms on your surface, and you also have the deuterium being sputtered more efficiently than the lithium. And then you also have chemical effects, which I also alluded to before. This is referred to as chemical sputtering, and it essentially results because the surface binding energy, which is some metric for how closely the surface atoms are held into the bulk material, is higher for lithium deuteride than it is for pure lithium. And typically, in sputtering calculations, you assume that the surface binding energy is equal to the heat of sublimation of the material. And so specifically talking about preferential sputtering now, if you want to look at where the deuterium atoms end up on a lithium surface, so we start with the simple case of a lithium lattice, and lithium tends to form a body-centered cubic structure, which you see here. And so you ask, where do the deuterium atoms adsorb when they hit the lithium surface? Well, you can look at various papers, and you see that there's three sites that are energetically favorable. One is on top of a corner lithium atom, one is in the so-called bridge site between two corner lithium atoms, and one is on top of the middle atom of the BCC lattice. And so you imagine that if they're on top, you have sort of a deuterium monolayer forming on top of your top surface. But if they're adsorbing deeper into the material, deeper into the first unit cell, then you have more of a homogeneous lithium deuteride material right near the surface. So whether you simulate this or this will actually give you different predictions for what the sputtering rate should be, for what the preferential sputtering rate should be. So it's something to keep in mind when establishing error bands on our prediction.
So just a dumb question. So this is relevant for a liquid?
So you still expect to have, so I agree that, so talking about, so you still expect to have adsorption for a liquid.
Yeah.
So this is obviously the case of a solid,
Yeah.
because this is a lattice. But you're extrapolating this to a liquid. And so you would actually, so you might argue that you expect something more like this for a liquid.
Yeah.
But in some cases, it looks like we actually will get a little something more like this, at least from the inferred erosion rates. And I'm kind of getting ahead of myself a little bit here.
But there aren't theoretical calculations for liquid.
Right.
So the preferential sputtering is because some of the lithium is kind of hidden underneath the deuterium. It's not the lithium density, it's not lithium atoms being displaced by the deuterium.
Right. Yes, that's true. Yes, that's true. Yeah, you still have the same amount of lithium. It's just you now also are introducing deuterium. And in this case, the deuterium is actually shielding the lithium to some extent. So the way that we actually calculate the reduction of the sputtering yield that occurs because of preferential sputtering is by using this ST-trim-SP binary collision approximation code. This is a very standard tool that people use in a lot of sputtering calculations. And you can incorporate preferential sputtering directly because you can actually specify the concentrations of deuterium and lithium on a monolayer by monolayer basis in the surface. So if you want to say I have, a half deuterium monolayer on top of the surface or something like that, you can do that. And you can in some way incorporate chemical effects by changing the surface binding energy of the surface. And so what I did is, for the purposes of changing the deuterium to lithium concentration, I linearly interpolated between the surface binding energies of lithium and lithium deuteride as a function of beta. So you incorporate the preferential sputtering, you incorporate the chemical effects, and you get this plot right here this is for the case of 20 eV deuterium ions incident on a lithium surface at normal incidence. And the blue curve, this is the lithium sputtering yield as a function of the deuterium to lithium concentration. The blue curve is that homogeneous case that I talked about on the last slide of no deuterium adsorbing on top of the lithium. And then the red curve is when you actually have a deuterium layer forming on top of the lithium surface. And so this actually implies very strong reductions of the sputtering yield. So you expect a reduction of about a factor of 10 in this homogeneous blue case, and a reduction of about a factor of 40 in the case of a deuterium monolayer on top of the lithium deuteride surface.
This is still assuming it's a solid.
Yeah, so BCA calculations are for solids. They specifically are sort of in the limit of room temperature. Although I'm going to extrapolate this to the liquid because that's basically, well, it's an assumption. And there's sort of no real sputtering codes that can actually directly simulate a liquid.
So if you've got 80% deuterium on the surface, you might have expected naively a 5%, a factor of 5 reduction in the deuterium. Deuterium over lithium concentration. It's 80%. Is that what you mean?
I mean deuterium to lithium concentration. So this is 50%, 50%.
Okay, so can you give us a physical feeling for why it's a factor of 10 in the reduction, or a factor of 40?
Well, you have to remember that there's also this surface binding energy reduction effect that's going on. So that incorporates an additional reduction into the sputtering yields. And it's not even entirely linear necessarily with the deuterium to lithium concentration, because the deuterium atoms are sputtered a lot more efficiently than lithium atoms by deuterium ions.
You're saying that the deuterium is much better stuck because it's mostly LID. But you see, even if I'm arguing that if the LID is 50%, if your beta is 50%, so this isn't beta down here, beta at the bottom.
This is beta, yeah, this is beta. Beta is the deuterium to lithium concentration. It's not the not whatever else you think it might be.
So what you're saying is that if they're 50-50, then it's 100% LID.
Yes, yes.
And why would you say that? Because you're just saying that it's...
That's the assumption. That's I mean LID, it's 1-to-1.
Or 1D.
I'm assuming that it all is precipitated as lithium deuteride and not, free-flowing lithium deuterium atoms going around. And there is evidence of that in the MD simulations.
You could have more D than.
Yeah, and after that, too, that goes negative or something. But a beta is 2.
So in Pisces experiments, they found that the maximum deuterium concentration they ever saw retained in a liquid was 1-to-1. And they did thermal distortion spectroscopy on the liquid layer, on the liquid layer after the experiment. And I mean, if you could go above 1, then yeah, in principle, this model would predict even stronger reductions of the sputtering yields. But experiments have suggested that that can't happen.
Well, part of that would just mean there wouldn't be any lithium.
Sure, yeah.
Well, your model already takes into account supersaturation of the surface, basically.
Right, it's taking into account, the red curve is taking into account supersaturation of the first monolayer, but you're assuming that under the first monolayer you can't have more than a 1-to-1 deuterium to lithium concentration.
I mean, sputtering also has this complicated thing where the particle comes in, it goes down a few monolayers, it comes back up, and really it's what blowing off as it's on its way up that matters.
Yeah, but that's all, this was done with the BCA code, so that's all taken into account.
So you're mixing every monolayer has the same beta, is how you're doing this?
Every monolayer, other than in the red case, the top monolayer is enhanced. And in the blue case, every monolayer has the same concentration. But you have to remember, these are very, you only have to simulate the first 50 nanometers or 100 nanometers. You don't need to simulate 50 microns of material or something like that.
Will deuterium sputtering rate go up as beta goes up?
Oh, yeah, because there's more deuterium.
So at some point, yield is going to be, total yield is going to go flat.
I would need to look. Generally, like ions sputtered or like ions much more efficiently than unlike ions, so probably the total sputter rate is going up. I didn't plot the deuterium sputter yield, but I do have that, obviously.
So I'm just trying to get my mind around this, at very low deuterium concentrations, then the lithium you're saying is just stuck to lithium, and that's easy to get off.
Yes.
Okay, I got it.
Okay, so we've talked a lot about sputtering. So what about evaporation? So the lithium vapor pressure above a mixed material lithium deuteride layer is reduced relative to pure lithium. This was not work I did. This is all existing data from a compilation of a number of chemistry experiments. And so the predicted flux of evaporative flux from lithium above the surface is given by the so-called Langmuir law equation, and it's just equal to the vapor pressure divided by 2 pi mkt. M is the lithium mass, T is the lithium temperature. And over here on the right, I've plotted the vapor pressure of lithium above a mixed material lithium deuterium layer divided by the anticipated vapor flux from a pure liquid surface as a function of beta. And as you can see, so the different symbols are different temperatures, and it's pretty much constant as a function of temperature, this reduction, which is good because it means that you can fit something very simple to it. So what I did is fit this empirical formula, which is just 1 minus beta to some power, and the fit is shown here in black. And so basically this establishes the very logical boundary conditions that there should be no reduction in the evaporation at beta equals 0. And I assume that it's completely, the experiments go up to determine the lithium concentrations of about 0.999-ish, 998 maybe. And they really seem like it's going to 0, so that was the motivation for this particular power law formulation. And so this 0.705 is a fit parameter. Okay, so now we can put everything together, and we have the flux of lithium from a surface. This is the total lithium erosion rate, and that's equal to the ion flux times F of beta, which is this deuterium to lithium mixed material reduction factor due to sputtering that I showed you a couple slides ago. And then this term is the collisional sputtering yield for room temperature solid lithium. It's reduced by a factor of 3 because experiments by J.P. Lane have showed that 2/3 of this lithium is sputtered as an ion, and so it's assumed to be immediately redeposited on the surface. It can't escape from the near surface sheath potential. And this term right here is the thermally enhanced sputtering due to the evaporation and sublimation of add atoms. This formulation comes from a paper by Russ Dorner on Pisces, and these coefficients y, a, and e are all fit parameters that I fit to the data from Pisces that I showed you on the second slide of the introduction. And so we're assuming basically that the so-called collisional sputtering yields and thermally enhanced sputtering yields are both reduced by the same factor F of beta, which is this mixed material reduction factor. And then you also have the evaporative term, which is reduced as a function of beta as well. And so what does this look like if you plot it as a function of the lithium temperature? Well, at very low temperatures, it's just a binary collision approximation sputtering, so it's constant. Then it starts to increase very quickly because the thermal sputtering term dominates. And then it starts to plateau between about 400 and 600 C. And physically, what this is assumed to correspond to is the evaporation rate of these add atoms actually becoming limited by their rate of production on the surface. And then it starts to take off again around 600 C or so due to evaporation. So the formulation of a model with liquid add atoms is a bit unorthodox, but they have actually been observed before in molecular dynamics simulations. And if you so this A parameter is related to the lifetime of an add atom on the surface, which is basically how long it spends diffusing around the surface before it recombines or sublimates off. And if you calculate it, you find that the tau for lithium is actually much greater than beryllium, solid beryllium. And physically this corresponds to, or physically this makes sense at least, because you would expect that a lithium add atom would have to diffuse around a very long time on a liquid surface to find a vacancy versus a solid surface. There would be a lot more vacancies. So you would expect the lifetime to be a lot longer.
So for the assumption that all of the lithium that's ionized is returned and deposited on the surface, there's going to be some that actually gets into the plasma, too, maybe small.
Well, I mean, there's an energy distribution of this sputter lithium, but it's, it peaks around 1 eV, and if you have, sheath potentials that are, 10 eV, 20 eV, something like that, there's not really much that's going to get out.
Yeah, I agree there's not much.
You've justified multiplying F of beta times y collisional over 3, I guess, because you did these sputtering calculations. What's the justification for multiplying it by Gardner's model?
It's an assumption that I'm making.
Because these add atoms are kind of not in the same, they're not really the same beast as the sputtering process from below, blah, blah, the sputtering process in the left part.
I mean, it's still a process that is a sputtering process in the sense that it results from ion bombardment of a surface and it's characterized by a yield. So, like I said, it's an assumption that I'm making.
Okay, to clarify that, when you say less vacancies on liquid, are you then saying some relationship between vacancies and the process by which then you have atoms bound on the surface?
Right. So, so basically, an add atom. I'm not sure if I exactly understand your question, but basically, an add atom, it is loosely bound. It goes through surface diffusion,
right.
And you would imagine with, I mean, a liquid is something sort of amorphous, so, it doesn't really have vacancies per se. So you would expect that it wouldn't really be able to find a vacancy to go into. So you would expect that it would spend a lot more time as an atom before it does find somewhere to go or it's sublimated off. Whereas for a solid, it can find vacancies.
Tyler, there was a competing thermal enhanced sputtering model that you thought about, the thermal spike one.
Mm-hmm.
Do you want to comment on how that one differs from the atom evaporation model?
Sure, I can. I mean, I didn't really talk about it because this model ended up fitting the data a lot better. So just in terms of making it a linear story. But basically, the thermal spike model doesn't have this one term right here. And so it basically says that erosion can essentially, or temperature-dependent sputtering can increase indefinitely rather than plateauing at some value. And so if you plotted the thermal spike model, it would basically sort of continually exponentially increase from 200 up to infinite temperature rather than having this plateau.
Is the thermal spike like a particle hits and heats up the little region of the surface or something?
Yeah, exactly. So it's typically applied in the high-energy heavy ion limit, and J.P. Elaine basically justified extending it down to lithium-lithium, deuterium-lithium type interactions because he claimed that the deposited energy density was still about the same. So he has a PhysRev paper on this. But like I said, the atom model seemed to provide a much more realistic description of the physics. Okay, so now we've talked a lot about modeling, a lot about theory, and now we're going to talk about the experimental apparatus and the procedure. So the apparatus with which to test these predictions was the Magnum PSI linear plasma device. It's shown here. And what this is a very large linear plasma device that can accomplish similar plasma parameters to what you find very close to the diverter strike point in the tokamak. And over here is the plasma source that generates your very high density plasmas. And then it shoots out in a beam that's collimated by these copper magnets here. It goes through a skimmer which pumps out almost all of the neutral particles in the plasma. And then the plasma beam strikes a target here. This isn't actually what my targets looked like, but this is you can just think of this as an example. And the experimental parameters were fluxes less than 2 to the 10 to the 24 per meter squared per second, less than 3 eV, less than about 10 to the 21 per meter cubed. We typically ran 5 to 10 second pulses, which was mostly limited by the ohmic heating of the coils. This resulted in magnetic fields of about 1/4 Tesla at the target. We generally bias the target negatively at either -20 or -40 to sort of establish the kind of ion energies that you expect in the NSTXU diverter. All the experiments I'm going to talk about with you were done at normal incidence, so normal magnetic incidence, so there was no magnetic presheath. There were 2 different sample types that I used. Both of these types were 2.5 centimeter lithium samples. The first was evaporated coatings using a prototype leader unit similar to the leader evaporators we use on NSTX. And they were less than 1 micron in thickness, mostly because it would take a prohibitively long time to evaporate longer or higher thicknesses. And then to actually get thicker lithium coatings, and I'll explain why we wanted to do that, we actually preloaded lithium targets, which I'll show you more about on the next slide. So as I mentioned earlier, we have the evaporatively applied coatings that are all less than 1 micron thick. And then I'm going to talk a little bit more about this because it was a pretty novel procedure. So what we did is we melted lithium into 100 micron to 1,000 micron deep wells, so wells that were just bored into a TZM molybdenum disk. And then we put these wells into an argon glove box. We heated up the lithium to about 400, 500 C, and the lithium melted into the well. We then used this little scraping tool to scrape off any excess. And then we put a thin piece of stainless steel shim stock over the lithium layer in order to prevent oxidation once we remove it from the glove box. You then put it inside a heat seal argon bag, and then we took it out of the glove box and shipped it over to Magnum PSI, which is in the Netherlands, if I didn't mention that already. And so when we put the samples inside the device, you then, right before you're ready to pump down, you take a pair of pliers and you peel back this piece of shim stock, kind of like peeling the lid off a sardine can. And this does result in some exposure of the lithium to atmosphere. Lithium oxidizes very quickly in atmosphere, and so it's exposed between 20 to 30 seconds. And so you could actually see the surface layers turning black between the cover removal and the vessel pump down. But then we ran some argon plasma discharges before the deuterium exposures to remove the oxide coating, and you could actually see the lithium become shiny again.
Would you recommend in the future that somehow we do this cover removal in vacuum or in an interlock or something?
That would be optimal. The logistics are obviously a lot trickier. That would definitely be optimal, yeah. Okay, so let me tell you about the diagnostic setup. So this is the plasma column here, and then this is the vacuum break right here. And so all of our diagnostics, for the most part, look through this one window, which is made out of barium fluoride. And so the main surface diagnostics are an infrared camera, which gives you a 2D profile of the sample temperature, and a high-speed visual camera, which has a lithium-1 filter on it, which essentially isolates this one very strong line radiation, the 3-to-2 transition in neutral lithium. So you can essentially measure the line integrated emission rate from lithium atoms alone. There was also this spectropyrometer, which is essentially an infrared spectrometer. So it measures all of the light in the infrared range from about 1.2 to 1.8 microns. And what you can do is you can fit a gray body Planck's law equation to the pyrometer data to get an emissivity independent measure of the sample temperature, which is useful because it's expected that the lithium emissivity is actually a pretty strong function of temperature. We also had a Thomson scattering laser to get very high resolution density and temperature measurements very close to the surface. So this was typically about 10 millimeters away from the surface. And an example radial profile of the temperature and density is shown here. So as you can see, it's pretty Gaussian with resolution of about 2 millimeters, maybe less than 2 millimeters. And so you can use these densities and temperatures to actually determine what your plasma flux is, which is nice. So before I get into a little more about the data analysis, I need to talk about one issue that we ran into during the exposures of the thick lithium films. So the advantage of the thick lithium coatings is that they should have saturated with deuterium much slower than the thin films. However, when we put these free surface lithium coatings into Magnum PSI, we saw a lot of melt motion and droplet ejection from the surface, which quickly reduced the coating thickness from its initial value to some other value where it was thin enough that the melt motion stopped and the droplet ejection stopped. And unfortunately, since it was now inside the vessel, we could not measure what this thickness was. So what I did was I took so this is a sample that was exposed to a single neon plasma shot, and the white stuff is all lithium carbonate. And so as you can see, it kind of got everywhere since it was just initially in this little cup right here. And so what I did is I took this one sample that still has lithium on it, and I measured, and then I took it out and I measured what the resulting thickness was as a function of position across the sample. And you use a technique called confocal microscopy, which is an optical microscope technique. And what I did, or I didn't do it, this was done by a colleague, Yawen Ye, who scanned across the surface from points A and points B in 500 micron increments, and basically found that the coating was very strongly reduced from its initial thickness of 500 microns. And it varied a lot, actually, from anywhere from about 10 microns to 150 microns, something like that. So basically, what this implies is that you need to model the deuterium lithium concentration as a function of time and temperature for some changing lithium thickness, which is a bit more complicated.
But you say assuming that coating expands during Z direction only during conversion to lithium carbonate, are you meaning that this is something that you assumed that was happening right after the plasma exposure, or something after you vented it?
After you vented, yeah. It's just because the density of lithium carbonate is about 30% higher than the density of pure lithium. So it's going to, 30% lower. So it's going to expand after it converts to lithium carbonate. So you take the thicknesses that you measure, and then you have to apply some correction factor. Nick.
It looks like there's a preferential direction here, maybe from one corner to the other in this figure. Is there any reason for that, or is it just?
Are you talking about these like spots right here?
It seems to be, yeah, quartered. It seems to be quartered.
Yeah, it was kind of strange. So it could just be so lithium wetting of metal surfaces is kind of complicated, and sometimes it seems to wet some areas well and not hold on well to other areas. And that's why I did a measurement on one of the thicker areas, which is point B, and one of the thinner areas. And
so this is still just normal incident field?
Yeah, this is normal incident field.
What position are you talking? Position millimeters on the left?
So that's position from the points as you scan to the left from these points. And so this is 25 millimeters, so this is pretty small, like basically about the dimension of one of these points or something.
Left to right?
From right to left. Yeah. And yeah, so this basically, all this melt motion basically motivates actually doing experiments with porous or mesh-like substrates where the lithium is more contained, and I'll talk about that in my future work. So if you have some thickness of lithium layer and you have some bombardment rate, what is the predicted deuterium to lithium concentration? Well, I talked about that a little bit already, but we can actually do some more specific modeling here. So first off, if you don't use deuterium, if you use, say, neon instead, then you don't expect any deuterium formation. So that's sort of the control experiment, that you don't expect any reduction in the erosion rate. And then you measure the erosion rate as a function of beta, the deuterium to lithium concentration. And I can predict what the deuterium to lithium concentrations will be using my model. And then I can plug those values of beta into the erosion rate predictions and see how it compares to the experiments. So this is what the predicted deuterium to lithium concentration would look like as a function of this time evolution of the deuterium flux and the lithium temperature that we measured. And I've plotted 3 different lithium coating thicknesses here, 25 microns, 50 microns, and 500. So 500 was the initial thickness, and then 50 and 25 are some nominal decreases. And so you get this sudden discontinuity at the lithium melting temperature, because as I mentioned earlier, the deuterium diffusivity tends to go up quite a lot once the lithium melts. Okay, so how do you measure the lithium erosion rate? Well, first off, you need to take your measurements of the lithium radiation, and then you figure out the lithium density. And so the way you do that is you solve the continuity equation for neutral lithium, and you end up being able to drop a lot of these terms because they are small relative to other terms. So S, R, and C are the rate coefficients for the processes of ionization, recombination, and charge exchange. And the S and R terms come from the A-collisional radiative model, which is an existing database of atomic physics data, atomic physics quantities. And they're plotted here for lithium as a function of density and temperature. And as you can see, in the parameter range we're talking about, which is sort of above 1 eV at densities of 10 to the 14, 10 to the 15 per centimeter cubed, the ionization is way higher than the recombination, so you can drop that. The charge exchange terms I haven't showed here. They're actually way off the bottom of this plot, and those are also small. And you can also assume the steady state, that is, that the lithium density is not changing as a function of time, because the ionization time of a lithium atom is something like 10 to the minus 6 seconds, and we're talking about experiments on the order of seconds here. So, and there were another number of other assumptions that we made.
When you're canceling R compared to S, it's not just the rates, it's also the relationship of the ion density to the neutral density.
Yeah, you're right, you're right.
And can you give us some sense of how well you knew that?
So, I mean, if you make these assumptions and then calculate them, it turns out that in all cases the ion density tends to be less than the neutral density. So there are a number of other assumptions that we made. So using the collisional radiative model is a pretty small error bar. Steady state, I mentioned, no recombination charge exchange. You assume that the lithium atoms are not diffusing perpendicular via collisions. That ends up being about a 1% to 5% error. You neglect secondary electron emission, which is a very good approximation because we have negatively biased targets. And then we also neglect radiation trapping, which is a process by which an emitted photon can be resonantly reabsorbed by the impurity species, but that's really only important if you're at very high neutral lithium densities, which we were not quite at in these experiments. But it is something that you would have to worry about if you went to even higher lithium densities.
What density is that term?
Well, I think it should just be linear, more or less. So if you went up another factor of 10, so if you're at like 10 to the 21 or 10 to the 15 per centimeter cubed, since I've been using centimeter cubed.
Now, radiation trapping isn't in the equation at the bottom, is it?
No, that's not something you need to put into the continuity equation. That would be something you need to worry about in inferring the lithium erosion rate from the density.
So the idea is that radiation doesn't get to you because it gets trapped on its way out.
Right, right. That would be the worry, yeah. So now that you have the lithium densities, how do you measure the erosion yield? Well, you solve this continuity equation with the simple boundary condition that the flux of lithium, or this is more of a definition than anything, the flux of lithium from the surface is equal to the erosion yield times the incident ion flux. So yeah, that's basically just defining what Y is. And then you solve for the lithium density. And then your model for how many lithium-1 photons, or what the lithium-1 photon flux should be, is N lithium times Ne times P, which is the photon emissivity coefficient, which is also a rate coefficient in centimeter cubed seconds that comes from the ADAS database. And so you have a model for how much lithium emission you expect as a function of Y. And so your only free parameter now is Y. And then you compare that to the measurement of the lithium-1 photon flux. And I've given some example measurements over here. As you can see, they're very radially symmetric. And so generally we radially average. And that's expected because, like I showed you before, the plasma profiles are symmetric. It's an axis of symmetry in the plasma. So you set the measurements equal to the model, and then you solve for Y, which is the only free parameter left in the equation.
How do you get V lithium?
V lithium, I assume, is equal to 1 EV, or the energy is 1 EV.
Just flat out independent of everything else.
Yeah. So I did some scans in what velocity you assume. It turns out not to really matter that much because the ionization mean free path is so short that it's just ionizing so close to the target that it really doesn't actually make that much a difference. So yeah, I didn't use like a full Thomson distribution like you might expect for sputtered atoms or a thermal distribution for evaporated atoms. But it turned out to really be, the results were very insensitive to what velocity you use.
And interestingly, the thing on the right does look very axially symmetric, and yet you showed us that surface that looked like who knows what all. So it's
This is actually averaged.
Has that been averaged or no?
No, the only thing I did here was correct for the tilted line of sight. The camera's tilted at about a 45-degree angle, so I corrected for that. But so this was for a thin lithium layer for something that was initially 200 nanometers. So no melt motion there.
Okay.
Yeah.
If you did this with the melt motion ones, were they more chaotic looking?
Yeah, a lot more chaotic looking. And generally, actually, the liquid pool in the center tended to actually be a pretty uniform temperature. So you actually saw a pretty constant emission rate from like the middle centimeter squared of the sample. Okay, results you've all been waiting for. So first, for the neon bombardment case. So this is the trivial case of no deuterium implantation. But the reason we used neon rather than something more conventional like helium, by the way, was we just basically didn't want any fuzz formation or nanotendril formation to occur, which tends to happen a lot with high temperature plasma irradiation with helium.
Including on lithium?
That's actually an open question. And there's actually, I think Magnum is actually doing some experiments, or did some experiments recently to actually see whether you still get fuzz formation when you have a lithium coating.
Not on liquid lithium coating, though.
Say that again?
Surely not on lithium. You can't get fuzz on liquid lithium, can you?
Oh, no, not on liquid lithium,
On the solid part.
yeah, whether the liquid lithium layer would protect the underlying solid from fuzz. That's an open question, but you certainly wouldn't get it on a liquid.
Okay, thank you.
Yep. So this is the erosion yield as a function of temperature. And so the amount of erosion you expect just from evaporation is given by this dashed line here. And I know these look like such amazing fits between predictions and data, but these are actually just fits I did to that at-atom evaporation model formula that I showed you earlier. There's no other, people have never done temperature-dependent erosion rates of neon bombardment of lithium before, so I didn't really have any other data to compare it to, but the fact that it is actually greater or equal to what you expect from Langmuir law evaporation is a nice sanity check that you are getting what you expect. And I guess I didn't put it on here, but if you calculate the expected sputtering yield with SD trim SP, they come out pretty close, at least a little lower than the experiment, but it's within the error bars. Okay, so what about the results for deuterium on lithium? So,
but what do you conclude from that? I mean,
so
the red one, you could say, oh, great, it looks like it's the addition of these two effects, and that's that. Can you do that with the blue one too?
Well, you also expect there to be a thermal sputtering term as well. So, and that's the unknown that I was talking about that we can't really compare with any past experiments. So the reason we did this, well, we're good scientists, but
you expect lithium to make its own atoms on a pure lithium surface is what you're expecting here? Is this what
no, the neon bombardment can induce the generation of atoms as well. It's not a phenomenon unique to deuterium. Okay, so what about the deuterium?
It didn't at 20 eV, but it did at 40 eV.
The effects seem to certainly be a lot more pronounced in 40 eV than 20 eV.
But that one almost looks like a linear addition.
Well, this is a log plot, but you talking about the slope here?
Well, I'm saying that it's at least converging to the evaporative one. The dotted line is the evaporated rate.
Yeah. Mm-hmm.
So it's converging to that. And,
right.
You know, it almost looks like its difference could be the sum of those two effects with no special add-ons. So.
Well, that would. It's pretty close to that, but it's not exactly that. I guess I didn't plot just that, but basically, I mean, the fact that you can see it's going up here, even, you know, since this is a log plot, this is still like an order of magnitude below this, and so there is a little bit of thermal sputtering terms. Okay, what about the deuterium case? So this is the atomic lithium erosion yield measured during deuterium plasma bombardment. So this was one of these initially 500 micron layers that I told you about before, but then you seem to get thinning via melt motion and droplet ejection to some smaller value, And the smaller value that seemed to fit best with the data was 25 microns. And so I've plotted the predictions of the atom evaporation model for the beta equals 0 case, so no deuterium implantation. 500 microns, which would have been the initial thickness, and then 25 microns, which seem to fit the data in terms of what the reduction in the thickness seemed to be. And the experimental data is given in black here. So you get good agreement quantitatively between the atom evaporation mixed material model and the data with the a priori assumption that the thickness is reduced to some smaller value from 500 microns. And the error band here is the difference between the homogeneous lithium-lithium deuteride model and having a partial deuterium monolayer on the surface that I talked about during the theory section.
That was about the thickness that you ended up measuring after the fact, right?
Yes, it is, Matt. Thank you for pointing that out. Yeah. During the confocal, during the confocal microscopy measurements, we measured anywhere from about 10 to 150. But if you average those, at least, it seemed to be on the order of 25, something like that.
How about the 200 micron layer coating? So we get into that.
200 nanometer coatings?
Nanometer.
Yeah, that's
whatever it was, the evaporative coating.
Yeah, that's the next slide.
Great.
Okay, so this is just so that was 20 EV deuterium, and this is 40 EV, and so that one looked very similar, and that actually seemed to fit best with a reduction to an even thinner layer of about 5 microns, but it looks
so now
relatively
is
similar.
the thickness, is that a fit parameter, or you assumed it ahead of time? Because you say a priori here, but then it sounds like you fit it.
It's a fit parameter, yeah.
Okay, so it wasn't Abrams.
Yeah, you're right. That's
These are the cup samples.
yeah.
Why the collisional level doesn't change in the beta equals 0 case between 20 EV and 40 EV?
It doesn't? Yeah, you're right. That must. You know what? I probably forgot to. I probably forgot to change it to the. Yeah, I probably forgot to change this for the 40 EV case. Sorry. But the temperature dependent term is assumed to be independent of ion. Okay, so what about the very thin film case? So for the thin film case, you would expect that basically the deuterium would saturate the lithium almost instantaneously. It actually happens within about a millisecond if you use the diffusion model. So you'd expect that you have the fully saturated case, the beta equals 1, throughout the entire temperature ramp up of the discharge. This is the lithium temperature versus the erosion yield for 3 samples that were initially 200 nanometers in thickness, but because they were so thin, they actually tended to deplete in about 2 seconds. So we were only able to get data for about 2 seconds of plasma discharge. But that's okay because the temperature ramp actually mostly happens in the first 2 to 3 seconds of the plasma exposure anyway. So the predictions of the atom evaporation model are shown here in blue. And again, the error band is the difference between whether or not you assume you have another deuterium monolayer on your surface. And so you actually seem to get pretty good agreement at very low temperatures, at sort of room temperature. Again, the ST trim yields seem to underpredict by about a factor of maybe 3 or so. And then at very high temperatures, up at 600, 700 C, you seem to be approaching what the atom evaporation model predicts. But in between those two, from about 300 to 600, you actually do have a discrepancy here. And the different colors are 3 different samples, 3 different lithium samples. So we did this experiment 3 different times, and we got consistency between the measurements, but not agreement with the model here. So the exact reason... Sorry, did somebody say something? The exact reason for this discrepancy is still sort of unclear. It's possible that you could have an increase in the surface binding energy for sort of monolayer level films. You would expect to get some adhesion and some material mixing potentially between the lithium and the underlying TZM substrate. But 200 nanometers is still many hundreds of monolayers, and so that's So like I said, the exact reason for this discrepancy remains unclear, and it's a future work topic.
What about the option of beta equals 7?
So, I mean, yes, you could match that with beta equals 7, but there's no physical reason. I mean, there's no physical reason to assume that that can happen. And I mean, I couldn't find any papers where anyone ever measured greater than 1-to-1 hydrogen to lithium concentration.
But you're in this dynamic situation where you're just feeding the hell out of it. And this very thin amount of lithium has been totally bombarded.
Yeah, it would seem like this is a candidate for an MD simulation or something, not a measurement.
Yeah, I agree. And
well,
I mean,
maybe you want to do both.
Well, no, but it's pretty hard to measure that.
Yes,
so it's going to throw away.
Yeah.
So you know.
Okay, yeah, fair enough. The underlying beta is not a candidate for measurement. Yeah. But your diffusion equation solution stops at beta equals 1 also?
yeah, so I mean, you basically assume that the deuterium starts to get reflected when you start to approach beta equals 1. So the reflection coefficient is inversely proportional to beta, or it's equal to 1 minus beta. So basically, if you're lithium deuteride, you're assuming you can't absorb anymore. Recycling is 1, if you want to use that parlance.
So I wonder if lithium deuteride, if you just keep feeding it deuterium, just kind of gets a lot of deuterium inside of its matrix too.
That's speculation, but yeah, that's possible.
Speculation. Okay, interesting. Okay.
Nick, did you have something else, or?
I think it's related. It's probably going to show my misunderstanding of this, but this temperature is also a temporal change. You're ramping the temperature.
Right. Yeah.
Is there any effect of that? I mean, does the plasma at 600 C know about what was happening at 300 C, and does your model know about that?
I don't know if I really understand your question.
Whatever is happening during the time evolution of this is going to affect like the width of your layer, and it's going to compound on itself.
Right. So
does your model just start at 600, or does it know that it came up through 300 and has been depositing?
Yeah. So you're saying, do I dynamically reduce the thickness as a function of time? Is that what you're asking?
Or do you suspect that happens in the experiment?
Well, yeah. The thickness is certainly dynamically reduced, but I'm assuming that it's uniform anyway. I'm assuming that you have complete saturation, but I am assuming that. I mean, the bottom line is that only the first few monolayers, or maybe the first 10 nanometers or 20 nanometers, matter in the context of erosion. So what's going on underneath is unimportant until the layer is actually depleted to where it shows through. Yeah.
So in time, there's just like that first millisecond where these conditions get initiated, and then it's pretty much
right
from then on.
Yeah, in this very thin case, or that's the prediction at least.
Is the temperature ramp linear? I mean,
no, it's sort of like a T to the 1/2.
Okay. So
it's all plasma heating. There's no external heating.
So the time it takes to get from 200 to 500, when your data starts to catch back up to your model, does that correspond to a certain amount of the sample that's been sputtered, so that maybe you could have lithium oxide at the top, because it's been exposed to atmosphere in the top half of the sample, and then you get down to a pure lithium at the bottom when your model is starting to be when your assumptions are starting to become more valid.
We don't really see any oxygen emission in these discharges if you look at the spectroscopy.
Really?
Yeah.
Any carbon? And those were evaporated in vacuum, not.
Yeah, so these are evaporated in vacuum. Remember, these are the in vacuo evaporation, not the preloaded.
Okay. Sorry.
So we didn't do argon discharge cleaning on these, but they were not exposed to atmosphere before.
Okay.
Would you expect to see oxygen emission if it was lithium oxide? I mean, is it possible that the oxygen and lithium could become unbound from the oxygen, but the oxygen doesn't become debound from the sample? Is there any reason to assume that might happen?
I mean, you would assume that the oxygen, I would think it would be disassociated pretty quickly in these sort of densities and temperatures that we're talking about. But we did also look for hydroxide emission, which is like 308 to 310 nanometers, and we didn't really see any of that either.
I'm asking because you see the decomposition of a lithium oxide on a molybdenum surface at 900 Kelvin. Just for instance, we've seen it in our lab, but you only see an emission of lithium. There's no oxygen because there's a process which enables for the oxygen to be retrapped before it's...
Okay. Yeah, maybe we can talk about this later. Keep in mind that this is a lot higher background pressure than your experiments. So
the first time we did these experiments with a much lower flux evaporator, there's a lot more oxygen in the films, and we did see oxygen emission in the plasma during those experiments. But then when we switched over to the liter evaporators, which have this huge flux compared to those small ones, it was pretty clean.
okay, so I guess I'm going to go through this slide pretty quickly. So we considered some other physics possibilities for why we could have seen such reduced erosion yields other than material mixing with deuterium. As I mentioned before, recombination and charge exchange should be small, but if they weren't, this would imply an even lower yield because basically you have another source of neutral atoms. We don't think the ion flux was getting reduced very close to the target, or at least it was fairly constant from about 4 to 20 millimeters out from the target. We did a scan in Thomson scattering measurements. And the ion current that you measured to the target also didn't really drop too much with the lithium on it. We don't expect drifts to be a factor because electric fields are all radial and magnetic field is nominally axial. So the drifts are all azimuthal, which is an axis of symmetry. The results, as I mentioned before, we talked about this already. The results were insensitive to erosion velocity. We measured the transmission of the optic system before and after the experiment. So, there was some concern that maybe the lithium was coating our windows, and so we were getting attenuation because of that. But the transmission actually didn't really change much before and after the experiments. And even if you did factor in lithium self-sputtering, which is assumed to be its small term since it's sort of a first-order quantity times another first-order quantity, this would imply an even lower yield because basically you're saying some of the sputtering was from lithium rather than deuterium. Okay, so we have finished with lithium erosion, and we are moving on to lithium redeposition. So this is only 2 slides. So lithium redeposition, as I mentioned before, is a process where a lithium atom is eroded into the plasma, it ionizes, and then it goes back to the surface as it follows the magnetic field lines. So you can infer lithium redeposition fractions, which is the probability of the lithium atom redepositing when it's eroded off, by solving the continuity equation for lithium 1+. So that looks like this. And we are assuming that the lithium atoms are quickly being thermalized by the plasma that is streaming along the field lines to the surface. And so it quickly obtains the ion sound speed velocity towards the surface.
What's the process by which that thermalization takes place?
Coulomb collisions.
With what species?
Deuterium and lithium plus. Deuterium plus and lithium plus.
Not the electrons?
No.
So it picks up so what do you mean by thermalize? It has the same temperature?
It has the same velocity as the deuterium atoms, as the deuterium ions that are streaming back to the surface. So this is actually an effect that they saw in Pisces, that they measured in Pisces. That basically they measured the Doppler shift. They looked at the Doppler shifts of some impurity. I think it was beryllium in a deuterium plasma, and they see that it actually picks up the velocity of the streaming deuterium ions as it goes back to the surface. But we didn't measure that directly here, so that's an assumption. So this is the formula for the redeposition fraction. As I said, it's the flux of ions back to the surface divided by the flux of neutrals from the surface. And so if you just want to do some simple approximations for what the redeposition fraction should be, So I just made some very simple Gaussian temperature and density profiles. So this is R over sigma. So sigma is the half-width, half-max. So it's sort of an independent measure, independent of the specific spatial dimension. So this is so both the density and the temperature measurements looked like this. And then you infer what the redeposition fraction should be. And for a temperature of half an EV, you get almost no redeposition. But because the ionization mean free path of lithium decreases so rapidly between 0.5, 0.75, 1, you actually get a very strong increase in the predicted redeposition fraction as a function of temperature. And at 2 eV, you have basically unity redeposition across the surface, actually a bit higher than unity, because some atoms are actually eroding from near the edge of the target and redepositing on the middle. And then near the edge, you get this decrease because some lithium atoms are still eroding off the edge of the target, and those are just assumed lost from the plasma.
So this diagram on the right includes ion diffusion.
This does not include ion diffusion.
Then how do we get bigger than 1?
Because the lithium atoms are eroded with a cosine distribution in polar angle. So
it's including a neutral diffusion, in effect. They come off as neutrals. You're saying when they come off as neutrals, they reionize and come back down.
Right. Yeah. I mean, that's not really diffusion since there's no collisions going on, but it's modeling the streaming. It's a three-dimensional calculation. So
geometric.
Yeah. Yeah.
Just that the neutrals moving around.
Right. Right. But then the ions only go. They only just follow the magnetic field line right back to the target. Okay, so how do the experiments compare with the data? So first of all, how do I measure redeposition fraction? Well, as I mentioned earlier, you start to see the lithium erode, or deplete rather, from the center of the sample after only about 1 to 2 seconds. So you can calculate at that depletion time, which I call tau, what is the total lithium fluence that has actually come off of the target. So that's this quantity in the denominator here. And then you compare that with the initial areal density of the lithium film, which I call rho. And it turns out that the fluence of lithium that you get off of the target is actually much, much larger than the initial areal density. And this is because of redeposition, or this is assumed because of redeposition. So your inferred R is 1 minus the areal density divided by the total fluence. And so those are these measurements here. And then these measurements out here near the middle of the sample are, you take the sample out after the plasma exposure, and you see that there's some circle in the middle of the sample that has no lithium on it, and then there's some portion here that still does have lithium on it. So the radius here is basically the minimum radius that still has lithium on it, and so you say, okay, what was the total lithium fluence that I saw from this ring right here? And then divide that by the initial areal density, and that gives you a redeposition fraction as well. So all of these redeposition fractions were very close to unity, greater than 0.99, and the predictions of the model are overlaid here. So basically I did some smoothing on the predictions, and then I did the bands here are the standard deviation from the actual variance that you actually see. But I smoothed it, and as you can see, the measurements so notice the suppressed zero here also. So this only goes from 0.98 to 1.02, and the experimental measurements are very close to the data.
The redeposition fraction being bigger than 1 on the axis can't happen after a while when there's no lithium left. No lithium anywhere near here or something, or is it still, it's the fraction density? But somehow if it's always positive, how can it ever go to 0?
Right, so the model basically assumes that there's always lithium all the way across the sample. So in some sense, the model is a simplification.
Right, I mean, couldn't you use the model to just deplete the lithium and see, and actually just model like that radius where it disappears? Did you try that?
I did not try that. So you're saying, I did not try that. And so you're saying, yeah,
A real brute fact about that is it's 2 centimeters of minimum radius. You blew it all away, and then it showed up somewhere else.
Yes.
It's interesting to see if your model did that.
Well, this data has not been published yet, so that's still a possibility.
Well, if it had been published, you get a second publication.
Okay, so I think we're running a bit late on time, so I'm going to skip the boron erosion measurements. This was only really preliminary work that we did anyway. And I'm going to get to the discussion and conclusions. Perhaps the most important takeaway from this thesis is how long will a lithium coating actually last in the NSTXU diverter, since that's what I was sort of paid to figure out. So the way that you can actually predict this is basically do a simulated series of, so the predicted current flat top in NSTXU is 5 seconds. So I did a series of 5-second pulses on a, so basically I assumed you had a thin lithium coating on a TZM molybdenum substrate. And so you modeled the thermal evolution of this layer, just basically using the thermal properties of molybdenum. It's basically, it's the semi-infinite limit of the thermal diffusion equation. And then for the heat flux, I use this formula from Stangaby, which is the heat flux is 1/2 gamma NETECS sine theta. Gamma is the sheath heat flux transmission coefficient. That was assumed to be equal to 8. Theta is the field line incidence angle. That I used 3 degrees for that. And then you basically dynamically measure, or you do the diffusion calculation along with the erosion calculation simultaneously. And you calculate, and include the redeposition fraction. So you incorporate all the aspects of the modeling and the prediction, and you basically dynamically model the deuterium concentration in the lithium surface as a function of time. And I also, so every time the lithium coating was reduced by more than 10%, I would actually revise the total thickness of the lithium coating and say that the rest basically had blown off into the plasma. This was a calculation that incorporated a lot of the elements of the theory of the modeling. And I should note that for the redeposition calculations, so I assumed that the maximum redeposition fraction you could have is 0.99. And the reason I did this is because you also have to worry about things like the transient startup and ramp down times of the plasma, where the density is a lot lower, and so the redeposition fraction is assumed to be a lot lower. And so since I wasn't incorporating those into the model specifically, I just set a bound of 0.99 on the redeposition fraction. So this is the predicted lithium coating lifetime as a function of density on the horizontal axis and two different temperatures, 5 eV. So 5 eV is the dashed lines, and 10 eV is the solid lines. And the different coating thicknesses were 1 micron, 10 microns, and 100 microns. So the sort of typical NSTXU diverter parameters you expect are about 10 to the 14 to 10 to the 14 per centimeter cubed. And so if you follow this up, you get something right in here for a 1 micron. And in this range, at least, the coating lifetime is pretty linear with the thickness. So the lifetime increases as the thickness increases by an order of magnitude.
These are assumed to be clean, or no impurities at all mixed in with the lithium? It's just pure lithium?
It starts out as pure lithium, but it incorporates the deuterium implantation, of course. Yeah. It doesn't incorporate oxidation.
Or carbon.
Or carbon, for example.
And so actually the experience of the old NSCX experience of lithium on graphite is, everything's different, right? Because there's the...
Yeah. I mean, this is assuming lithium on TZM.
So actually, we should be forbidden to even dream of comparing this to the NSCX experience.
Yes, you should.
Okay.
Well, you did do experiments on graphite substrate.
Yeah, so we did. I mean, we did do experiments on graphite substrate, which I didn't include mostly just because of time constraints. And I mean, you see that the lithium emission rate very quickly decreases, which is indicative of the lithium intercalating into the graphite matrix. So you don't actually maintain the pure lithium coating on top of the graphite to be eroded into the plasma.
Thank you.
Yep.
Here you're assuming 3-degree angle of incidence for the field lines, but your experiments and your modeling are done with normal incidence. Why is that relevant?
So it is, in some sense, an approximation, but I think, like I say, if you got to the, I don't know how far you ended up reading, but so basically at these sort of parameters, you're actually going to have a very high fraction of prompt redeposition. So essentially the ions are going to come back, or the lithium ions are going to come around on their first gyro orbit and actually redeposit basically right under where they eroded. And at these, so maybe that's not totally relevant down here, but up here at sort of, NSTXU, sort of 1 Tesla type fields even, I think the gyro radius is going to be something like 1.5 millimeters or something like that, and the ionization mean free path is even less than that. So they tend to just promptly redeposit. So in some sense, it's a decent approximation.
I mean, the other reason you could argue that it's relevant is that the sheath basically confuses the angles of incidence, and so your ions are coming in at effectively normal incidence anyway, even in a 3-degree field.
Yes, yeah, that's true. And also I should mention, for the purposes of the erosion calculations, I used for the collisional sputtering yields, I did do simulations at 45 degrees, so I included that effect.
And the other thing is your principal processes of erosion are coming off with the normal or cosine distribution.
Mm-hmm.
So the angle feeling doesn't matter for that either, as opposed to like a backstriding or reflection will matter.
Yeah. Mm-hmm. Yep.
So if you start on the right-hand side and work left, you're kind of going up steeply, and then it kind of slows down to a linear. Then at 10 to the 13, it completely changes and crashes down, and then goes to a plateau. Now,
Okay.
Can you identify?
Yeah. All right. So
what's physically going on?
So there's a lot going on here, and I didn't want to get into going into all of it, but so basically, first of all, if you went to even lower densities, this is obviously going to go up again, because then you're at even lower fluxes, and so it takes an even longer time to deplete. But those are pretty irrelevant. So here, so it's more or less constant, and then this increase is more or less because the redeposition fraction is increasing very strongly between about 10 to the 12, 10 to the 13. And the other thing you have to think, so here you're in the quote-unquote linear regime, where the redeposition fraction is already 0.99, so it's already maxed out, and then it basically decreases linearly because the density is increasing, and you basically expect the erosion rate to be, it's proportional to density because it's proportional to the flux. And then up here, so at this point the PFCs are actually starting to get pretty hot, and so you have evaporation occurring also, and you also so it's a balance between whether the lithium layer can actually become saturated with deuterium before it fully depletes. Because if it gets saturated with deuterium before it depletes, then the erosion rate all of a sudden goes way down. But if you're way up here where the erosion rate is just too fast, then the lithium layer is actually just gone before you can actually get significant saturation of deuterium in it. So that's why up here it starts to get all kind of nonlinear with density and temperature.
But the temperature is a kind of hidden variable.
The surface temperature, yeah, I haven't plotted that here.
Yeah. So it's increasing intensity.
Sorry, say that again?
The variable isn't just density, it's surface temperature.
Yes, yeah. The variable, because the yields are dependent on temperature, beta, and the ion flux. So
you haven't fixed the heat flux. In the Q equals so-and-so, you're fixing T, not N? Or, whatever. What are you fixing in that?
Well, I'm varying them both because I plotted two different electron temperatures, 5 eV and 10 eV. And then, that CS is obviously related to those.
So,
and then
so essentially what's happening is the heat flux is going up by orders of magnitude as we go along.
Yeah, the heat flux is changing.
But weren't they paying you to do their actual neutral beams? I would argue.
Say that again?
If you had much more heat flux than we actually have power, that would be a problem.
Well, the highest case is, the highest case is a heat flux of, I think it's around maybe 10 megawatts per meter squared, about as high as you get. But these cases are, the cases here are, maybe like 3 to 4 megawatts per meter squared. I would need to look it up exactly to see what it is.
It's certainly, you've got n times t varying by some significant, or n times t to the 3/2 varying by some very large factor across that line.
Yeah, that's very true.
One might be interested in sort of what's a for some realistic heat flux, whatever that means, to sort of identify points along this curve that are sort of realistic heat fluxes.
Right, so that's why I'm saying that sort of in here are the realistic NSTXU diverter densities and temperatures, and correspondingly the realistic heat fluxes.
I see, okay. And then finally, so that everything is really dependent on this Rmax specified at 0.99, or a lot between 10 to the 13 and 10 to the 14.
Sure, yeah, it's proportional to 1 over, I guess it's 1 over 1 minus, if you want to solve this for tau. But yeah, it's dependent on 1 over 1 minus r. So, if you go to 0.999, then it increases by a factor of 10.
And your justification for 0.99 is?
It was a somewhat arbitrary decision. But the lowest values I saw in experiments were about 0.995, so I rounded down.
Okay. Make sure why experiments is... To think through why the experiment would be relevant to this, your modeling actually was bigger than 1, just to confuse the issue in some cases. Okay.
Sure, yeah, it's a different geometry, so, you'd have to model the specific geometry. All right, so summary. So I developed this at-atom evaporation mixed material model using a lot of existing data and some new data to predict the temperature-dependent lithium-deuterium erosion rates. And then I developed techniques for inferring the time and spatially dependent erosion yields of these mixed material films using ADAS atomic physics data. I then measured the erosion yields of lithium and boron coatings on TZM molybdenum during high-flux plasma bombardment. The model was observed to capture the quantitative dependence of lithium erosion yield at least for the case of the control case of neon and the thick mixed material lithium deuterium layers, and the boron erosion measurements, which I didn't show you. Okay, conclusions. So, if significant quantities of deuterium accumulate in a lithium coating before it depletes, the lithium erosion rate will decrease dramatically. Lithium will redeposit in NSTXU diverter plasmas with a probability close to unity, and the combination of the suppressed erosion and the very high redeposition efficiency strongly indicates that existing lithium temperature limits on this high Z substrate should be reevaluated. And I predict that the lithium coatings in the NSTXU diverter in that density and temperature range that I showed you are predicted to last 50 seconds per micron.
So we had a lot of discussion, but are there one or two last questions for the speaker?
I just have a quick one. Sure. Sorry. I want to go back to oxygen just really quickly. With your samples that you had, the macroscopic samples, did you ever run a control test or anything on just the black surface to see how the lithium oxide layer might behave differently under the sputtering test than argon clean lithium?
I guess, So the thing is that once the lithium melts, that's going to start diffusing into the lithium surface. So I guess maybe in that there might be a small range before the melt layer breaks through the coating that you could see a difference, but I didn't look for it.
I think there's some papers I've read that show that oxygen stays on the surface of liquid lithium just by free energy.
The segregation effect?
Yeah.
Yeah.
So maybe it would last a little.
Yeah, again, we don't see oxygen on the spectroscopy measurements.
I saw that.
Yeah.
So if you go back to your conclusions, the one, and I think a lot of this is clear enough, the one in boldface there. So the temperature limits were normally set by people just thinking about evaporation, I think.
Yes.
And you get lower than evaporation because the lithium deuteride has a lower SBE.
A lower what?
A lower surface a higher surface binding energy, pardon me.
It's not so much of a, well, I don't know if that's exactly the way to talk about it. I mean, that's chemistry, and you have the formation of lithium deuteride, and every compound and element has some vapor pressure curve as a function of temperature, right. And its curve is a lot lower. I'm not sure whether you can call that, whether that's a surface binding energy effect, really.
It's related. But
related, sure, yeah.
So essentially what you're saying is that this stuff is altering into lithium deuteride, and so it doesn't evaporate as much as you might have otherwise thought.
Yes.
Okay? Mm-hmm. But then you told us that lithium deuteride has a melting temperature.
Sure.
So this would be I'm actually just trying to put bounds around this to understand it a little better. There's some temperature range over which this should be a big effect, but then I would think once lithium deuteride, that those bonds don't count anymore, then it would return to being the evaporative limit.
That you would approach the evaporative limit. I mean, you're
normal previously thought of evaporative process, I guess.
That would have to be investigated, and you'd have to get up to 700, 800 C to investigate that. Yeah.
But you think at the sort of 500 C level, where people have been moaning about, oh my God, too much lithium, they may be missing by a couple orders of magnitude at the point.
Exactly. Yeah.
Excellent.
Okay, let's thank the speaker one last time. I'm going to ask all of the faculty and staff and postdocs to remain in the room for discussion and invite the speaker, students, and guests to await us in the
to enjoy the pleasure through the hallways.
Enjoy the pleasure through the hallways.
Students ready to go into the theory.
Fine, should we go to the theory?
Thank you, Darren. So the final get together is actually going to be in the theory lounge, so you guys can